So hey everyone, welcome to the first lecture of DFS and its applications. So this is the first video of the series here. So as this is the first video, let me just explain what we'll be doing in this series is that we'll be solving some good rated like 1500 to 1800 rated problems related to basic application like you must have. So the prerequisite is that you have to be familiar with the DFS, BFS concept and some the graph terminologies like what is undirected graph, what is directed graph, what are nodes, what are edges, and after that you can come to this series. Here we'll be discussing some good applications of DFS and graph and how to solve 1500 to 1800 rated problems of like related to those concepts like graph and DFS. So the first problem of the series would be Hongkow builds a nation. So let's directly get into the video. So what the question is saying is Hongkow is the ruler of the world, and as the ruler of the world, he wants to make it easier for people to travel. But like this is just storytelling. We are given undirected graph and node M edges, and some of the nodes, like K of the nodes, are home to governments. Like there are some special nodes, and these governments make up the world. So what makes so just read this question once by yourself, and I'll be just briefing upon like if you didn't understand the question. So what makes a graph stable in this question, what makes a graph stable is that there should be only one edge between two nodes. That's the first condition for a graph to be stable, and no edge should connect to itself. That is self loop concept. There shouldn't be a node connecting to itself. And furthermore, any two nodes corresponding to government, that is any two special nodes, we are just calling them special nodes as of now. Any two special nodes should not have a path, like there shouldn't be a path from one special node to any other special node. So that so these are the conditions that makes the graph stable. Now Hongkow wants to add as many edges as possible to the graph while keeping it stable. So determine the maximum number of edges Hongkow can add. So this question is easy, like if you are if you are good enough in DFS, and it just needs very small observation. So let's directly get into the solution. I'll be explaining the problem with a small visualization first, like what we have to do, and then we'll be directly getting into the solution. So now let's get into the solution. So let's just say you are given these nodes. Um, this node, let's just say you have one this node and this node. Okay, so now to mark them special, let's just say this node is special, uh, this node is special, and yeah, these are the only two nodes that are special. So as you can see, the graph is already stable. As they said in the question also, the given graph will be stable, but still we are asked that how many more edges can we add? How many more edges can we add so that the graph still remains stable? So now let's just take the ink as blue. So if you see closely, I can join these like this node. I can join this node, I can join this node, I can join this node, and I can then join this node with this one, this node with this one. You'll understand why I'm doing this. This node with this one, and this node also with this one. So basically, all the nodes from this particular node to all the nodes to this graph. Similarly for this node also. So let me just make it much more clear. I'll just make this graph up here. 1 second. So suppose these were the two nodes, and these are and both of these nodes are not special nodes. So we can connect this node to this node, this node, this node, and this node. Similarly, this node can be connected to this node, this node, this node, and again this node. So this is the maximum answer possible. You cannot connect this particular node to this node. That is not allowed, because if you connect this particular node to this node, then if you see closely from this special node, you have a path to that special node which will make your graph unstable. So that is not allowed. You can't connect this one, like this particular connection is not allowed. Why it is not allowed? Because then you will have a path from this particular node, you'll be able to go to this node, and from this you'll be able to go to this. But the condition for a graph to be stable was you're not allowed to go from a special node to a special node. That there shouldn't be a undirected path. So this was the question. Now what's the idea behind the question? Let's look at that. So first, let's just focus on some concepts. So suppose I tell you that this is the graph. This is the graph. So so let's just break this down into some smaller sub problems. If we're given a graph, let's just say of n nodes, so what are the maximum edges you can have? Maximum edges you can have. What are the maximum edges you can have? So the factual answer for this is n into n minus 1 by 2. You can run test cases, but if you want proof, that is also easy. The proof isn't that tough. You can just take a look at the proof yourself. So the maximum edges for a graph with n nodes is n into n minus 1 by 2. So after knowing this fact, please try the problem by yourself, because that's how I'll be giving you the editorial. Like sub problem, like we'll be breaking the problem into smaller sub problems, and then you can try yourself. Then again we'll be breaking into smaller sub problems. So the maximum edges here we have is n into n minus 1 by 2. So let's just say what all are possible here, what all edges we have here. This is possible, this is possible, this is possible, then again this is possible, this is possible, this is possible. Yeah, I think that's it. Now if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we had 1, 2, 5. So 5 into 4 divided by 2, which will give you 10. So as you can see, for given there are n nodes, maximum edges possible is n into n minus 1 by 2. So this is the first hint. Now we'll be using this fact, like this is a very important fact for a question. Let's just say what we'll be doing is we'll be calculating the maximum edges possible. Given the graph, we'll be calculating the maximum edges possible, and then in the end we'll be simply returning m minus maximum edges. Sorry, maximum edges minus m. Like these were the maximum edges possible. We already had m edges, so the remaining edges you can add. This will be the concept of a video. Like this will be the main idea. So the main idea is to calculate what are the maximum edges possible. So let's again get back to the question. Let's take the red one again. So let's just say we are drawing again. So here, and then let's just say we have a 2. So now let's mark some of them as special. Let's just say this is special, this is special, this is special, and out of these two, none of them are special. So now let's get to the main idea. Now what? After this, now what we have to do? So you are given these edges. So let's just number these edges: 4, 5, 6, 7, 8, 9, 10, 11. Okay, so you are given 1, 3 and 6. Like you are given that these are the special edges, 1, 3 and 6. So what you have to do is, you know that you cannot connect this graph with this graph. Like these are these should be disconnected. You cannot connect these graphs. So what you'll be doing is you'll simply run a DFS in this particular node. Like you'll be iterating over this array, and you'll be running a DFS for this particular node. After you run a DFS for this node, so let's just run a DFS. You'll come to 1, you'll come to 2. Always make a count of the number of nodes you have visited. So let's just make an array for that. You have 2 nodes visited. Then like I'll show you the code also. Here you have 3. So again start with 3, go to 4, again come back to 3, go to 5. So you made a count that we have 3 nodes over here. Now let's come to 6. From 6 we went to 7, we came back to 6, then to 8, then to 9. We were counting, we have a total of 4 nodes over here. That's it. This will take care later. This will be a different case. So now we can see that in the first connected component we have 2 nodes, 3 nodes and 4 nodes. And you know that these nodes are 2, 3, 4 have to be independent. You cannot connect anyone. Like you cannot make this connection. This connection is not allowed. So once you know that connection is not allowed, Now if I tell you there are two nodes over here, again let's take the concept. If we have this component, how many more edges can I add? Right, so our idea is we have to calculate the maximum edges. So let's make a global maximum edges is equals to 0 as of now. So if we have two nodes, let's use a formula, 2 into 2 minus 1 by 2. The answer is 1. So max edge plus 1. Again, we have three nodes. So what is the maximum possible? 3 into 3 minus 1 by 2. 3 are possible. But we don't care that we have two nodes. Like as you can see, this is a possible connection. But for now, just ignore that. We know that there has to be three edges. So plus 3. Again, four components. So 4 into 4 minus 1 by 2. This will give you 6. So plus 6. We are just keeping count of the maximum edges possible. Later on you'll realize why we were doing this. So once we have done this, now we know that what is the count? 10. What is this 10 basically? This 10 is basically all these imaginary connections that we have not made. All these imaginary connections. So if you count 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, one more connection has to be there. 2, 2, 4 minus 1, 6, right? From 7 to 6, 7 to 9, 7 to 8. Okay, 1, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so if you count all the edges in this particular section now, we have a total of 10 edges. Now, what to do with this? 11 and 6. Suppose you also had a 12th node. You also had 12th node, but this is like now whatever is left, like the nodes which you have not visited. Listen closely. The nodes which you have not visited can make a connected component themselves. Like if I know that 11 is remaining, 10 is remaining, 12 is remaining, and let's just say 13 is also remaining, you know that these nodes are not part of any government because they are not connected to any special node. So all you have to do is you have to also keep track of the unvisited nodes. So let's just say in this case the unvisited nodes are 1, 2, 3, 4, 10, 11, 12, 13, 4. And again, let's use the same concept, 4 into 4 minus 1 by 2, again 6. So we know that we can make we can connect all of these now. 1, 2, 3, 4, 5, 6. So again, so let's add again plus 6 because we can connect these, right? These are not part of any government. You cannot connect any two government to government because then you will be giving them a path, and you cannot give them a path. You cannot give a path from a special node to another special node. So once you have taken care of that fact, now let's move on. You have also made a connection of all the unvisited nodes. Why you're allowed to do that? Because that is not hindering with a stable condition. Again, because these are just independent nodes. They are not they have nothing to do with special nodes. Now still some edges are left. After this answer is 16, still some edges are left. We can connect this particular group to one particular node. Like you cannot say that, one second, just erase this. Like you cannot say that let's join 10 to 8 and 11 to 4. This is wrong because again you gave you again connected two special nodes. Remember, this is an undirected graph. You again connected two special nodes and you're not allowed to do that. That is the stable condition, that you're not allowed to connect two special nodes. So you're not allowed to do this. So now you also must have gotten the idea that you can only connect all of them to one connected component. Like either you can connect all of them to all of the third component, yeah, all of these nodes to all of the second component, like it's your wish, but it has to be only one component. You cannot connect one node of this, so let's just call this remaining nodes family. So if 11 decided to go to 7, then all of them have to go to this family only. Let's just say this is family 3, family 2, family 1. You're getting right, because then this is allowed. 13, 12, everyone is connected to this particular family. That is allowed because then you are not connecting any two special nodes. So that was the main idea. You're not allowed to connect any special nodes. So now how to decide which family to connect? That's the second condition. How to decide which family to connect? It's pretty obvious that you have to go to the family which has the maximum number of nodes, right? Because suppose I selected this family, the family 1. So now 11 would be connected to 1, 11 would be connected to 1, and 11 would be connected to 2. Like you just added 2 more edges. Similarly, 12 will be connected to 2, 10 will be connected to 2, 13 would be connected to 2. But if you would have selected family number 3, if you would have selected family number 3, so if you would have selected family number 3, then 11 would have connected to 7, 6, 8, 9. Like 11 would have connected to 5 nodes, 12 would have connected to 5 nodes, 10 would have connected to 5 nodes, 13 would have connected to 5 nodes. So you got 20 extra edges. So that's the main idea. You have to keep track of the family which has the maximum number of nodes. And after you have counted what are the remaining nodes, just join them and then connect all of the so let's just call this remaining family. The remaining family will connect to any one of the families, and which family would that be? The one with the maximum number of nodes. So this was the whole idea. I'll also show you the code now, but let's just revise one last time. What's the first thing? Just revisit all the ministers, like all the government special nodes, run a DFS, make a count of the nodes, make a count of the nodes in them, and count the max. The main motive is to count the maximum edges, and then later on subtract them with the m, like subtract that with m. Then you know what extra edges you can add, because m is already given, right? Max edges minus m will give you the extra edges that you have to add. So once you know that 2, you know that there would be 1 edge. Once you know 3, you know there would be 3 more edges. Once you know 4, you know there would be 6 more edges. After this is done, you have made the connection between all of the families. Like each member of the family is connected to each, like another like a family is connected completely. Like it is like everything is connected now. Something like this. Everything is connected. Once you have made this connection, you go to the remaining nodes which are not part of any special node. Then you also connect them, because that is not creating any issue with your stable condition. And once you have done that, you can connect this remaining family to any one family. And which family would that be? The one with the maximum nodes. So this is the whole idea of the problem. uh, Now let's look at the code for this. So the code is also simple, like it's not that complicated. First I've read. So what is the C? The C is basically the maximum possible. The C is basically the special nodes. There are k special nodes given, right? First you read the special nodes. Once you have done that, make the graph. Once you have made, I have made an adjacency list. So make the graph, also make a visited array. This would be helpful to later on create that remaining family, because the remaining family are those nodes which are not visited at all after you have traversed over all the special edges. What is this maximum edges? This is what, so if you see in the end, I'm printing maximum edges minus m. So this is maximum edges. What is the maximum node count? This is the node count of the maximum family member, like node count of the maximum family member, maximum family count, you can say. Like in our case, it was family number 3. You can say family number 3 has a total of 5 nodes. So in our case, that maximum node count would be 5. So now once you have done that, let's iterate over k. As I said, you have to iterate over the special government nodes. Node count, always before running DFS, make sure to make the node count as 0. We don't need edge count. Make sure you make the node count 0, run a DFS. You can see DFS is pretty simple, just node count plus plus, like the standard DFS template. Visited is true, if not visited, run again a DFS, and node, like always keep doing node count plus plus. Once you know the number of nodes, you know the maximum edges is node count into node count minus 1 by 2. Again, to keep the track of the maximum family count, you will be doing maximum node count is equals to max of node count comma nc. Once you have that, Now we need to count these members. This is our next task. We have to count these, the ones which are not at all visited after visiting every government node. So how to do that? Just iterate over your visited array, and if something is not visited, that means that is a part of the remaining family. Now join all the unvisited. What's non-visited? Should be unvisited. Uh, 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 Join all the unvisited, non-visited, whatever. Join all the unvisited nodes. So how much edge? So what is the count of edges that would add? It would be again be not visited into not visited minus 1 by 2. Basically, this line 211 is this. Like you saw, right? I joined 11 with 12, 12 to 13. Like if you're given four remaining nodes, how many edges can you join? So that is 4 into 4 minus 1 by 2. Once you have that, now this is that thing. 212 line is I'm connecting all these nodes. So I'm connecting all these nodes with this family. So how many edges that would add? Suppose in your remaining family you have 10, 11, 12, 13. Right, this is what you have. And in your family 3, that is the maximum count family. One second. Okay, this is not getting erased. So in your maximum family you have 6, 7, 8, 9. So again this 10 would be getting connected to 6, 7, 8, 9, 4. Again 11 would get connected to 6, 7, 8, 9, again a 4. 12 would be getting connected to 6, 7, 8, 9 plus 4 plus 4. That is 4 into 4. So once you have a count of this family member, so NC is node count of family 3 into node count of this remaining family. That will be your answer. Like that would be again you have to add that to the answer. So again you saw maximum edges plus equals to not visited into maximum node count, and in the end just simply print maximum edges minus m. That is your complete answer. So I think it should be clear by now. Just again, like this was a bit clumsy, but still just rewatch the video. This should be clear. Like this is the core observation. Maximum edges minus m. Maximum edges, you know, right? Because we want what in this given graph, the shadow edges. Like what we were given was 7, 6, 9 and 8. But this we also want to count this. And these edges, after adding these edges, that is getting counted in max edges. And then we are subtracting m. So that would give me the count of these dashed edges. We basically need the count of these dashed edges. And this edges, the dark edges, these are already given to us in m. So if I do max edges minus m, I'll be getting count of these dashed edges. So that was the whole idea behind. The only core was to count this maximum edges minus m. So yeah, thank you for watching. I'll upload the code in the description. Yeah, thank you.